neural networks, since that has been, and still is, I think, a debatable subject. But first, let's look at acute coronary syndrome. Like Paul said, it was basically an effect of the artery in your heart being clogged up by plaque. And it's difficult for you to see here, but this yellow stuff here is the plaque that gets into the wall and makes the accessible volume to the blood in the vessel less accessible, basically. Which means that the blood cannot transport oxygen to the muscle cells. And in the end, this will produce muscle necrosis. And that part of the heart will actually die. And that will never reform. So this is something you will have to live with. And there's an early stage of this called ischemia, which all of us actually have to a certain extent. And acute coronary syndrome is either acute myocardial infarction, which is a heart attack, the deadly stuff, or unstable angina. Now, the heart generates electric activity, right? And what starts that electric activity is an activation potential in this region of the heart called sinusoidal mode. This triggers the contraction of the surrounding muscle cells. And their contraction triggers other muscle cells to contract as well, creating a cascading event of contracting muscle cells. And this is actually what pumps the blood through the heart. And we can actually read this electric activity using an ECG. And what we typically get is this time series of electric activity that you see here, as the muscles contract during the heart. And we record this in 12 different ways, called 12 different leads. And these leads view the heart from different angles, which gives us a better image of the entire activity of the heart. So, this is a graphical representation of the model that I've been working with primarily. This is called an artificial neural network. And that is basically a set of nodes connected via weights to each other. These green guys here are called input nodes. This will actually have the features that we extracted from the ECG. So this will typically be an ST elevation, and this might be a duration in the signal. And then we feed that into something what we call a hidden layer, which we then feed out to an output layer. And this output layer will give us a probability of a patient having acute coronary syndrome. And that's what we compute. And the trick with these guys is we want to compute the magnitude of these vectors. And this is a mathematical representation of what you see here. And this is the only formula I will show during this presentation. Now, I haven't used a single neural network. I've used ensembles or committees of individual artificial neural networks. And the way we build those guys is that we have the entire data consisting of this huge green block here. And then we sample from this data, creates a smaller block, and we build an artificial neural network ensemble on that guy. Then we sample again, build a new network, sample again, a new network, for as many times as we like. And what we then do is that we combine their outputs to form an average decision. Basically, it's like going to City Hall and voting. Everyone gets a vote, and everyone is weighted equally. And all we can hope is that the majority decision is better than one individual decision. So democracy rules here. Now, naturally, I think artificial neural networks are kind of cool, and they can do a lot of good stuff. But everyone does not agree with me. There was a guy called A.K. Judy in the late 90s who claimed, and I quote, "Although neural nets do solve a few toy problems, their powers of computation are so limited that I'm surprised anyone takes them seriously as a general problem-solving tool." And I think that I'm one of the guys who have proven him terribly wrong, and many others. Now, we talked before about evaluating the performance of an artificial neural network. The way we do this in the thesis is actually that given that we have a trained neural network ensemble, and we have a bunch of people with acute coronary syndromes here, and we have a bunch of healthy control subjects here, we take a random sample from these guys and push that through the ensemble, get an output, basically a probability of having the disease. Then we do the same for the healthy subjects. We get an output here. The AUC, which is the area under the receiver operating characteristics, tells us the probability of the sick people having a larger predicted risk than a randomly chosen control subject. And this makes sense, right? Because if this probability is 0.5, that means that it's basically just flipping a coin, which is not acceptable, of course. But if this probability is 1, then we have a classifier that never does anything wrong. It's perfect all the time. That has never happened to me. I'm aiming for it still. And if this probability is below 0.5, we need to find ourselves a new job, because then we actually modeled the wrong task. But to dive in what an explanation really is, given that we have a good prediction, we trust the prediction, right? We know that the patient comes in and the neural network says this guy is 80% certainty acute coronary syndrome. The question now is why? Our view on this is actually highlighting the features most important for this decision. And this is a small toy example. Say that we have a number of patients here for which we have age, sex, smoker status, diabetes status, troponin levels, BMI, and cholesterol levels. Now the first guy here has a probability of 80% of having acute coronary syndrome. And the answer is because the age could be high. He is a smoker, and the cholesterol levels are high. So that's what you should look at. That's the reason. And now the physician needs to go in and interpret this in their own way. So basically what we do is that we trust the expertise of the well-trained physicians, but we point out the direction in where they should look basically. Now for the last one here, it might be that the age is not so high, and also the person is a female, and the troponin levels and BMI is okay. That means that this person has maybe a 30% risk of acute coronary syndromes. And that would be the explanation in that case. Now, in our work, we mainly used features from the ECG and not these kind of features. So let's dive into the papers. The first paper was actually a proof of principle, where we wanted to see, can artificial neural networks actually be used to predict acute coronary syndromes in the clinics? And as well, we wanted to compare it with a more established statistical method called logistic regression. And we wanted to compare these guys to see how similar are they? Do they look at the same risk factors? Do they produce the same probabilities? Are they calibrated? And what's their average performance compared to each other? So basically, we studied the AUC and the calibration, the odds ratios for the different input features, as well as some correlation analysis on the probabilities that they produce. And now for some funky stuff. The question is, how do we make sure that we don't trick ourselves? I could just take a data set, right? And I could split it into training and a test set. And I can build a model on the training set, and I can test it on the test set. And it's good, fine. But the thing is, if I have made another partition, the test result might actually differ, which means that we need to do this multiple times to gather statistics to be sure that this was not produced by chance. And the way we do that is that we take the entire data and divide it into k parts, called an outer cross-validation. And within that validation, we build models on the k-1 parts, and we test on the part that we excluded. And doing this by repeating n times, we actually get n times k performance results. And looking at the average or the median value of that, we should be pretty close to the truth. So the neat thing here is no information leakage. We always test on data we have never seen. So this is the result from paper 1. We had an artificial neural network as well as a logistic regression model. And this is the receiver operating characteristic curve. And the area under these curves is the measure I explained with the red guys and blue guys. And as you can see here, the artificial neural network ends up at 81% of the area under the RC curve. Meanwhile, the logistic regression ends up at 76%. So, to conclude, we would say that ANN and logistic regression show promise to be used as a clinical prediction tool given that data. And also, both models are actually well calibrated, which means that they produce good probabilities. ANN was slightly superior in performance, and they actually agreed on the same risk factors as well, which means that the ANN and the logistic regression model looks at the same things, but the ANN may be able to find some hidden nonlinear information, because that's what ANN really does well. It finds nonlinear information that may be hidden from the human eye or from linear models. In paper 2, we want to check, is there an optimal subset of the 12 different leads that we can look at? Or rather, how many leads do we need to make accurate predictions of acute coronary syndromes? And the rationale here is, why would we want to throw away information? Well, there are situations where the 12-lead electrocardiogram can be impractical, because for that, this particular 12-lead, you need 10 different electrodes that you attach to the body. 1 on each extremity and 6 on the chest. And these are the results. If we look at the best individual lead, how well that performs, that was the lead ABL. And it actually performs rather well, 76% area under the RC curve. If we look at the best 3-lead combination, we find that it ends up at 82% of the area under the RC curve. Meanwhile, if we use all 12 leads, we end up at 81%. And now every logical person cries. Why is this? This does not mean that throwing away information makes us better. This only tells us that if you have a kid and you throw candy all over the place, the kid will have difficulty deciding which candy to pick, right? But if you throw only one candy, he can pick it immediately and everyone's happy. And this is what happens with the neural networks. In this case, we have too many candies in the forests. There are so many ways to be happy that you don't know which is the most happy. So we say that there are limited options of being happy, that those are very good. So in summary, 3 leads are actually sufficient for the prediction of acute coronary syndrome. And this is a major improvement, of course, because instead of attaching 10 electrodes, you could do with 4 plus 1, so that's 5, which is much better, of course. And important here is that this result does not apply to physicians, because like I said before, artificial neural networks are very good at finding nonlinear information that is hidden from the human eye. But it is useful for decision support systems and situations where the 12-lead ECG is impractical, where you have access to computerized interpretation. In paper 3, we want to compare the best methods to estimate the performance of a neural network. This was a numerical study where we compared 5 different sampling methods. We compared 5-fold cross-validation, bootstrap, and holdout using 3 different cuts. The dataset we used were myocardial infarction, that we discussed before, an acute coronary syndrome dataset, we looked at breast cancer, we also looked at 2 simulated datasets. And the way we did this was that we took the entire dataset and divided it into a training set and an independent test set. And this independent test set was huge, because this would be the notion of our truth. And on this training set, we provided a performance estimation loop where each of these guys came in. That produced 25 test results. And the closer the average of these 25 test results came to the test set, the better the resampling method was. And the results are actually that the 5-fold cross-validation and holdout gives good average performance. But they do feature large variance, which means that we have a lot of different predictions, but on average, the performance is just right. The bootstrap estimator is positively biased, which means that it overstates the performance, basically. So in the end, we recommend using holdout 0.25 and 5-fold cross-validation, which is a tad surprising because holdout is a very, very simple resampling strategy. In paper 4, we wanted to check, what's the best way to predict acute coronary syndrome? Or rather, who is the best at predicting acute coronary syndromes? And we had 4 different evaluators here. We had clinical experts, 2 well-trained clinical experts that does this on a daily basis. And we had the traditional ECG criteria, and we had ANN ensembles, and the standard statistical logistic regression model. So this was done on 861 patients attending Lund University Hospital. Actually, 862, but one of them were kind of freaky in the ECG, so we removed him. And two expert physicians classified each ECG into 1 of 3 categories: no signs of ACS, possible ACS, and ACS. And we did a feature selection on the whole material. Now for the results, this is surprising, because remember that ANN beat logistic regression the previous time. This time it was the other way around. The logistic regression model had 88% area under the RC curve. Meanwhile, the ANN followed closely with 86. But more surprisingly, the expert panel, the top-notch physicians, they end up at 78% of the area under the RC curve. This means that the models are actually 10 percentage units better than the physicians in classifying acute coronary syndrome from ECG data alone. This does not take into account blood samples and does not care about clinical features or reading the patient's looks and stuff like that. This is only given the ECG. And that's important to remember. This is not to replace physicians. This is to provide another predictive tool. And the ECG criteria ended up at 76%, the lowest, of course. So in summary, ANN and logistic regression has superior predictive performance on ECG data compared to expert physicians. And the limitations here was that the feature selection was done on the whole material, and we also had few classification categories for the expert panel. And both these things could actually reduce our performance slightly, but not as much that it would change the conclusions of the paper. Now for the last 2 papers, so I will combine them. These 2 papers relate to, given that we have a trained neural network and we trust the predictions, how do we extract explanations so we can explain them back to the physician? So what we did was we developed and explored 4 new methods for case-based explanation. And we evaluated the algorithms on the electrocardiography data from the former study, and we also had 2 synthetic data sets called months 1 and 3. And the good thing about these guys is that we know at any given time point which variables are important for the prediction. And we benchmarked against expert physicians, and we also checked agreement between methods and physicians, within methods and within physicians. So basically we had 4 explanation methods. One is where we always treat the network as a black box actually. But in the first one, we punch each and every one of the green balls, which are basically the input variables to the machine learning algorithm. And the more effect that has on the outputs, the more important that variable is. And by punching each and every variable in turn, we can create a ranking list among these variables to which is most important. We also use the generalized odds ratio, which means that we check how the odds of having acute coronary syndrome changes when we change one of the input variables, which will also produce a ranking. Then we had another wild guess that we started out with that turned out to be very useful actually. That is that we look at the distance between a given patient and the decision boundary, the boundary separating the sick from the healthy guys. And the farther away, the more confident we are in that prediction. And if we decompose the distance into its components, the components that are the farthest away are the ones that were the most important, the most certain that this prediction is actually true. And in the iterative input clamping, what we do is that we actually take a walk from the decision boundary to the patient by clamping one of the inputs one at a time to see the importance they have on the output. So for each evaluator, which was the expert physicians or our explanation methods, we select the top 5 important features for each case for the ECG data, and the top 3 important features for the monks data. And then we check overlaps and distribution of selected features. So just to benchmark and make sure that we're doing something right, we tried on the monks data, where we know the truth. And here, the best method actually provides correct rules, or actually correct explanations, that is, in 95% of the cases. Meanwhile, in general, all the methods do well in more than 90% of the cases. So we know that it works now, okay? So now we wanted to see what kind of features on the ECG data do the physicians select, and what kind of features do the algorithms select. And this plot actually describes that. Here we have the 12 different leads, and here we have the measurements within each lead. So effectively this gives us an illustration of all the variables we have. And we can see here that the physicians use all of the ST information, which is this section here basically. Meanwhile, the methods only used these 3 variables of the ST section, which means that our neural network can find all the information it needs from these 3 alone, because we know that it predicts at least as well as the physicians. And a neat thing as well is also that all of them agree that negative T waves are important, and this is actually a classical sign of acute coronary syndromes. Now, the overlap, what is that? That is basically, given a physician and given a method, they both select 5 important features. And then we check how many features are present in both their rankings. And that can be a number from 0 to 5. And on average, or median really, that overlap was actually 0, both between physicians and between methods. And that is of course disappointing, because that means that everyone disagrees. No one agrees on anything. So then we thought that these kind of measurements are very correlated, which means that they're not extremely dissimilar from each other. Which means that we can reduce the whole ECG down to an effective set of features using correlation analysis. And then the overlap dramatically increased actually. Now we came up to a comparison between a given physician and a method. In median, they had an overlap of 3, at least 3. Meanwhile, the physician versus the physician had an overlap of 4. So 1 more variable that they agree on in median. Meanwhile, the methods agree incredibly between 5 out of 5 possible, indicating that they're not really that different. So in summary, the proposed explanation models have the potential to be used in conjunction with AN in the clinical decision support systems. And even though the methods do not agree with the physicians, maybe that is not the worst thing, because the physicians do not agree either. And the problem here is the gold standard. How do we know what features are the real ones to look at? That is not entirely easy, because it could very well be that the neural network finds features that are very important to medical science that has not been discovered yet. And this needs to be investigated further. So the overall thesis conclusion is that AN ensembles are better than expert physicians in predicting disease from ECG data alone, not given the look on the face of the patient, or blood samples, or clinical features, or things like that. And we can also explain the predictions from the trained AN ensemble. However, we need to test this further. But we're 1 bit on the way at least. And the gains are obvious. We can have consistent predictions that does not depend on how tired the physician is or how many patients it had during the day. And also we can provide a second opinion to the physician that will always give another view on the prediction. And in the end, we can, from those 5%, it could end up with saving more lives. And particularly, we could avoid unnecessary hospitalizations. And this is, of course, a major cost benefit, where the hospitals can save a lot of money. Which means that we save a lot of money as taxpayers, which people usually like. So for the future work, we need to make prospective studies on the effects of decision support systems. This has to concern multiple centers featuring several thousands of patients over a lot of years, basically. And this way we can actually do temporal and spatial validation. That's just fancy names for time and geographic separation. And in the end, we need to perform randomized controls trials indicating improvement in patient treatment due to clinical decision support systems. And I'm actually confident that in the future we will see a lot of this.